First lecture is Justin Brown, and he's going to tell us about the roots of independence and multi-set polynomials.
Thank you, Bill. It's a pleasure to be here. I'm going to be talking about some joint work with a number of people: Carl Dilcher, Carl Hickman, Richard Hoshino, Richard Nowakowski, all from Dalhousie, where I'm from, Hugh Thomas, also from, and Dave Wagner as well, all of us from Canada. So I'm going to just begin. There are many polynomials that are well known in graph theory. We've seen this all last week. Chromatic polynomials, a number of people have spoken about. Network reliability, which is where I started in graph polynomials, which, as Alan told you, it deals with a model where all the vertices are always working. It's the edges that are independently operational with probability p. And you ask, what's the probability that you have a spanning tree? And flow polynomials, we've heard about. All of these polynomials arise from particular applications, and the fact that they're polynomials just seems to happen. And what I want to put forward is that if you have any sequence of numbers associated with graphs or any combinatorial structure, forming the generating polynomial, of course, is one way to examine the structure of such sequences. And in particular, the nature of the roots will tell you something about those sequences, even if you're only interested in the combinatorics. For example, this is where I get to use Isaac Newton's name here, which I want to bring into the talk. If you haven't seen this result before, it's one of the most beautiful results, I think, that connects combinatorics with analysis. And it's an elementary one, and it says the following: suppose you have some sequence of positive terms, and you can loosen that a little bit, but in most applications what we have is a sequence of positive terms that count something, each term. Then the sequence is unimodal, that is, it's non-decreasing than non-increasing, so in general it rises to a peak and falls down. If the polynomial, the generating polynomial, the sum of the ai's times x to the I, has all real roots. And this to me is a fascinating theorem because it somehow connects up the realness of the roots with really the structure, the combinatorial structure of the numbers that you're looking at. And Doran Zeilberger, a combinatorialist, says that what combinatorists love to do is to prove that sequences are unimodal. It's one of the things that they all love to do. And of course, sometimes it's easy to prove directly that a sequence is unimodal because it's symmetric, so you have to prove that it has a peak in the center. Or you know where the peak is. The interesting thing about this theorem, due to Newton, is that it allows you to say that the sequence is unimodal without knowing where the peak is, simply by knowing that the fact that all the roots are real.
Does this hypothesis actually imply that the sequence is log concave?
It does imply that it's log concave, and so if the sequence has no internal zeros, then in absolute value, the sequence is unimodal. Yeah?
Does the converse hold?
Does the converse hold? No, it doesn't hold. No. And so you can't hope it to get at everything that you'd want to prove about unimodality by looking at the realness of the roots. And in fact, what more is true, that you don't really need the roots to be all real. What you need the roots to be is in a certain sector of the complex plane between 2 pi, whose argument is between 2 pi over 3 and 4 pi over 3. And that includes the negative real axis. So that's a more general result. And again, that's not a necessary and sufficient condition. There are examples of polynomials that are unimodal that don't have all its roots in the complex plane. But the key thing here, I think, is that even if you're just interested in proving unimodality, then you are somehow drawn into looking at the nature of the roots and the location of the roots in the complex plane. And I'll just mention that an easy corollary of this is you can give your students, if they've seen this theorem, to prove that the binomial coefficients n choose I are unimodal. You get it in 1 second just by looking at the generating polynomial. Okay, so the location of the roots and the nature of the roots of such polynomials are of interest, even if you're only interested in the combinatorial properties of such sequences. Okay, so what I'm going to do is I'm going to focus in on two combinatorial sequences. One is going to be generating functions of independent sets of a graph, and the second of open sets in a finite topology. And I think, as you've heard Alan say before, certainly the generating polynomial of independent sets of a graph has a physical interpretation as from the hardcore model. We'll talk a little bit more about the second later in the talk. So I'm simply going to define, let G be a graph, finite and undirected. Then the independence polynomial of G is defined to be this generating polynomial. I sub k is the number of independent sets of size k in the graph, and you're multiplying it by x to the k. Now, a little bit of history about it. Independence polynomials have cropped up in isolated places in the literature. Alan has mentioned a result due to Heilman and Lieb talking about matching polynomials. And essentially what it says about independence polynomials is that if you look at independence polynomials of line graphs, they have all real roots. And in particular, what you get from that, of course, is that the sequence of independence numbers are unimodal. And so an interesting corollary there. There's another result due to Fisher where he looked at, instead of independence polynomials, he would look at what he called dependence polynomials, which are a sense looking at generating functions for the number of cliques in a graph of each size. And he proved this interesting fact that the root of smallest modulus is real. And it's a very interesting proof that he has. And so it's cropped up in a few places throughout the literature. So I want to focus in more on this. And my interest was, I came to Dalhousie University, and in Halifax, for some reason, there's a little hotbed of interest in something called well-covered graphs, which are graphs where all the maximal independent sets have the same size. And I had come from a background of graph polynomials, and it seemed to me that simply looking at whether a graph was well covered or not, whether all the maximal sets had the same size, was too particular, and it would be much more interesting to look at how many independent sets you had of each size. So that, and I'll come back to that a little later. You could ask, what about calculating this polynomial? And like most graph polynomials, it's difficult to calculate. And in fact, with my student Richard Hoshino, we showed that determining the value of the independence polynomial at any z other than 0, and at 0, of course, it's 1, because it's got constant term 1, is NP hard, even when you look at a class of graphs called circulants, which are Cayley graphs. Okay, so some examples. Of course, for the complete graph, you don't have any independent sets of size 2. So the polynomial is 1 plus nx. For the complement of a complete graph, every subset is independent. And you see that it's just 1 plus x to the n. For C5, of course, you've got one independent set of size 0, the empty set. Each vertex is independent of size 1. And if you look in the complement to this graph, you've got 5 edges. They correspond to the independent sets of size 2. And there are no other independent sets. So that's the generating polynomial there. For the bipartite graph KNN, you get 2 times 1 plus x to the n minus 1. And in particular, you see from the third example, the roots don't always have to be rational. From the fourth example, they don't always have to be real. And finding formulas for independence polynomials, just like with graph polynomial, with chromatic polynomials, are often non-trivial. We have a formula here. My student Richard Hoshino and I looked at circulant graphs, and this is a circulant. The vertices are Zn. You join 2 points along the outside if their distance, mod n, is at most d, and you get a formula like this. And one thing that we noticed, it had an interesting application to guitar playing, in the sense that in music, what you want is you've got a scale, The common scale is called a 12-tone equally tempered scale, so 12 tet. And typically what happens is you want certain pitch classes to be forbidden in a chord because they're dissonant. They're too close in frequency. So that's modeled really well with a circulant. And in particular, we can allow the number of notes in the scale to grow. And so this will give us a count quite easily of how many consonant chords you have in an n-tet scale. So we're going to ask what we can say about the nature and the location of the roots. And so for the rest of the talk, I'll be talking about mainly some problems and some results. So one question that seems like a natural question to ask is if you look at all graphs of order n, how large in modulus can an independence root be, a root of an independence polynomial? And so myself and Richard Nowakowski came up with the following, which determines it up to the proper order. Let beta greater than or equal to 2 be fixed. Let r sub beta of n be the maximum modulus of a root of the independence polynomial of a graph of order n with independence number beta. And then what we find out is r of beta is essentially n over beta minus 1 all to the power of beta minus 1 plus some smaller ordered terms. And you could ask, is that best possible? And in fact, we found a family of graphs which approach that bound. And the family looks something like the following. You essentially divide n up into sets, beta minus 1 sets, each set of size approximately n over beta minus 1. So it's a1 up to a sub beta minus 1. You put a clique on each one of those. The last one has some extra vertices if some are lying around. And then you join a new vertex v to all vertices of each one of the cliques except for the top one. So then what we need to do is we need to calculate this. Remember, we're looking for a root of large modulus, which can be tricky to do. So you have to think, how are you going to find a root of large modulus? Well, if we're lucky, hopefully the root is real, and then we have more techniques to use. And in fact, what we get is the polynomial. This is an explicit determination of the polynomial. And we did a bunch of calculations, and we noticed that if you looked at the number minus L to the beta minus 1, and L is approximately n over beta minus 1, then it has sign at that point, at that value of x, of minus 1 to the beta minus 1. But you check that the polynomial has sign minus 1 to the beta as x goes out to negative infinity. So you get a root out to the left past this point. And when you do a calculation, you find out it has the right size. So for fixed beta, that gives you the answer of how large the modulus can be. We could ask about special families of graphs. And I'll just put up a few results by myself and Richard Nowakowski. If you have a graph with independence number beta, that's the line graph of a tree, then all of a sudden things really shrink. They no longer depend on n. And in this case, what we get is the independence polynomial has a root of modulus at most beta choose 2. Now, the real starting point for me for entering into independence polynomials was this notion I mentioned earlier of well-covered graphs. A graph with independence number beta is well covered if all the maximal independence sets have the same size beta. And I'm just going to, as an aside here, is there a chalk brush up here? Maybe not. I'll use a different part of the blackboard.
It's down underneath the...
Oh, I see. Yeah. If you have a set x, a finite set x, you say that C, a subset of the power set of x, is a complex if y is an element of C, and Z is a subset of Y, implies Z is an element of C as well. That's the notion of an abstract simplicial complex simply being closed under containment. What you find out is that almost all the polynomials you've seen before arise as certain polynomials, which are called the F polynomials. F of C of x is written as the sum of fi x to the I, where fi is the number of sets of size I, which are typically called faces, in C. So if you write out the F polynomial, which stands for the face polynomial, for a simplicial complex, chromatic polynomials arise in this way, network reliability polynomials arise in this way, and independence polynomials arise in this way. The complex for an independence polynomial is simply you take x to be the vertex set, and C is the set of all independent sets. And simplicial complexes extend the notion of a matroid. A matroid is a particular simplicial complex that has what's called the exchange axiom. So it's even broader than matroids. Okay, and there's a notion of a complex being pure, which means that all the maximal faces, all the maximal sets in C have the same size. And it's weaker than being a matroid. Every matroid is a pure complex. Well-covered graphs correspond to exactly saying that the independence complex is pure. So it's sort of, and that's where I saw the F polynomial might be of interest. So the original starting point for myself was the following theorem. Myself, Carl Dilcher, and Richard Nowakowski, all the roots of the independence polynomial of a well-covered graph G with independence number beta lie in the annulus, that should be modulus of Z, between 1 over n and less than or equal to beta. And I think the key thing here is that it's bounded by beta. Remember, for general graphs, it depended on n, and was looking something like n over beta minus 1 all to the beta minus 1. And here, it all of a sudden shrinks down to beta, and with a root on the boundary if and only if G is complete. The bound of beta is indeed the best possible. And this is an interesting story, which if you're just starting out as a researcher, I advise you to work with a colleague where you have to discuss things over the telephone. Because my colleague and I were talking about it. He had an idea for a graph that would approach the boundary. He explained it to me on the phone, and I completely misunderstood him, and I invented a completely different family of graphs. Turned out that his family that he had suggested actually didn't work out, and my misunderstood family actually was the examples that we were looking for. So that was really lucky. What we're going to do is we're going to form a graph LK of beta. You take all k tuples where the elements are 1 through beta. You join 2 if and only if they agree in a coordinate. Okay, now this gives you can check. It's not too hard to see that this has independence number beta. In fact, it's well covered. You get a formula for it, and that formula looks like it's going to be pretty much hopeless to look at the roots. But what we could actually show is that all the roots of LK beta are always real and negative. Of course, they're going to be negative for any of these polynomials. And that, in fact, if beta was between 1 and 2 to the k minus 1, which we could always ensure by choosing k large enough, then the smallest zero, the zero most to the left, will lie pretty close to minus beta. And this is the only factor front, and that's going to 1. So, in fact, those would be the examples that we needed to find. And in fact, these polynomials are related to one classical or orthogonal set of polynomials, namely the Legendre polynomials. And in fact, we could prove all sorts of things about it. The coefficients are unimodal, of course, because the roots are all real. And in fact, we could find that the peak gets closer to beta minus 1. So it's going to be near the end. Okay, and the distribution of the roots. So where are the roots in the complex plane? We've seen a similar question answered for chromatic polynomials by Allen that said that the roots are dense in the plane. A little fact that's pretty easy to show. There's an operation that if you work with perfect graphs, you would have seen before. It's the notion of taking a vertex in a graph and replacing it by another graph. I like to think of that as a substitution. Sometimes it's called the lexicographic product. And the independence polynomial is well behaved for these. So if you want the independence polynomial of G where you substitute for every vertex H, it's the independence polynomial of G where you substitute for the variable x, the independence polynomial of H with the constant term removed. So that's fairly straightforward. And in fact, the closure of the roots of independence polynomials, we could use that to show not only are of positive measure, they actually, again, cover the whole complex plane. By myself, Carl Hickman, and Rich Novoskowski. And it says that the independence roots of this family, so you substitute for every vertex of these graphs that we saw before, a clique, and then you substitute for every vertex an independent set, they're dense in the plane as n and m and k vary. Okay, so there's something interesting going on with the behavior of independence polynomials at lexicographic products. And in particular, if you take repeatedly doing the lexicographic product of a graph with itself, you again get independence polynomials, and they're related to one another in a nice way. So this was one of those fortuitous times where I sat down at the computer not really knowing what to expect and tried plotting the roots. And this is what I got where I substituted for P3 itself 11 times. And of course, I'm sure all of you recognize that's got to be a fractal. And so that was the starting point of looking at these repeated products. Yep.
Were those computed? Those roots were computed?
This was computed, yes.
What was the degree of your polynomial?
Now that's an interesting question. It's a high degree polynomial, so how did I find the roots? What you can do is when you look at it, because of the way the substitution works, you can simplify searching for the roots as what you do is you set the polynomial equal to all the previous roots, and you solve for each one of those in turn.
May I suggest that what you've got there are the effects of round-off error? What? Of round-off error. I'm not, because that's something you would typically, I mean, I'll show this afternoon, and you can get some incredible patterns. And those are, that to me,
Well, this is
yes, it's a fractal, but I think it's more related to the fact of effects of round-off error, which are highly correlated. They're not independent.
this is the Julia set of the polynomial that you're iterating.
Yes, exactly. This is the Julia set. So it is indeed a polynomial,
Yeah, but if it's done by,
a fractal.
if it's computed by round, if it's computed,
Right.
my only point is, you may be right, but I wouldn't jump to the conclusion that what you see is a fractal, but it may be due to round-off errors. I mean, I'll show some examples that have got very similar patterns, and I know the roots exactly. You know, what I get are fractal patterns, what look like fractals. So, yes, you have a fractal, but I'm not sure that you've isolated the correct cause. That's my only point.
Can I make a comment? I think Itzikson and maybe Derrida or Zubair did a related study of complex temperature roots, and I think they're correct, the results are correct, and they did get fractals, so that's in a sense a defense maybe of.
Right, and I think the thing is the polynomials, because I'm not getting high degree polynomials when I'm solving for the roots.
And
I'm saying a low degree polynomial and searching
And
for
they were
many
doing
roots.
hierarchical lattices, which is very much in the spirit of what you're
Well,
doing here.
that's what he has also.
Yeah,
Right.
so I believe your result, actually.
Right. Okay, I'm going to continue. I take your point. So fractals arise, and in fact, what we do is we looked at a reduced polynomial where we got rid of the constant term. It simply makes things a little bit simpler. We define this set being the limit in the Hausdorff metric of the roots, and in fact, what you get is you get the Julia set of the polynomial, and it's equivalent to being the closure of the union of the roots.
Reduced independence polynomial again?
Yes, it's
Subtract one?
we got rid of the constant term. Just makes things a little bit simpler. So here are just some of the fractals. There's another example. And one of the questions that we looked at was whether they were connected or not, and break up into fractal dust. And I'll just put up a few theorems here that illustrate. In some cases, we could answer the question of when it's connected as a fractal and when it wasn't. And in particular down here, the independence fractal of copies of KB is connected if B equals 2 and A equals even, and otherwise we could show it's totally disconnected. So I'll just show a few pictures. There seems to be a nice variety of what the fractals look like. This is one of these examples that are totally disconnected. And this is another one that happens to be connected. Okay, and we've extended them to simplicial complexes. Now, don't think I'm going to get around to open set polynomials, so I'll end off on here. Well, maybe I'll take a few minutes just to talk about it. What we looked at was another example that really I hadn't seen much before of what would you do, and it was mentioned yesterday, if you wanted to look at some notion of a random polynomial. Okay. And what we did here was not quite random. We looked at what was the average of the independence polynomials over all the graphs of order n. So natural thing, I think, to look at, and I think there's only one paper about that for chromatic polynomials. Now, of course, that won't necessarily be an independence polynomial. And along the lines yesterday, I think someone was asking, what about polynomials, chromatic polynomials for random graphs? So here we did look at what could we say about independence polynomials of almost every graph. The independence polynomials of almost every graph of order n we could show has a non-real root. But the average independence polynomials we could show are have simple real roots. So somehow they don't reflect, of course, you might not expect it, but we weren't sure what to expect.
Would that be true? I mean, you used the random graph G n 1/2.
Right, you did.
But would this result be also true for GNP?
I think it's true for GNP as well. Okay, so I'm just going to very quickly. There's another thing that I looked at are something called finite topologies. If you've taken point set topology, it's made up of open sets. Open sets are closed under union and intersection. Of course, if it's a finite set X, then there's only finite intersections and finite unions. In particular, the finite unions and they're related to directed graphs. They're related to directed graphs that are what are called preorders. They're transitive and reflexive. And because there's a nice bijection between the two of them. Here's a finite topology. And what you can do, again, is if you're interested in open sets, which are the basic constructs of finite topologies, you can form the generating polynomial. Now, in terms of combinatorics, if you look at these preorders, which are related to partial orders, you get what are called ideal polynomials, where d sub k are the number of downwards closed sets in your digraph, your reflexive transitive digraph. So there's an example of one such polynomial. Notice some of the terms can be missing, which you don't get in really any of the other polynomials that we've looked at. It's simply because in a finite topology, you don't need to have open sets of all cardinalities. Okay, so what can we say about the roots of these polynomials? I'll go down to the bottom here that if the finite topology has cardinality n, then the roots of the open set polynomial have modulus of most 2n. And that's not best possible because what we find out if you have width 1, which looks like a chain with some cliques substituting for them, then you actually get the golden ratio as being the best possible. Okay, and in fact, on the other end, if you're looking at finite T0 topologies of partial orders, you get a root of not as big as 2n. The best we can do is about n over log n.
Is this the Lambert W function?
It's exactly. It's really exactly that. Okay, and the roots are dense in the complex plane. And I'll just end off in the last 30 seconds on the. Here are some open problems. I don't make conjectures readily anymore, since the Brown-Colburn conjecture is false. Was a paper. Question: when are all the roots of the independence polynomial real? Again, you've heard that Seymour and Chodnovsky proved that it was real when G was claw-free. When are the roots of an open set polynomial real? Nothing's known about that. What's the maximum modulus of the open set polynomial? When is the independence fractal of a graph connected? And lastly, what is the closure of the roots of the open set polynomials when you ask about T0 topologies, which are exactly the partial orders? Yeah.
Yeah, about question 4.
Yes.
I'm more interested in the clique polynomial, which is the independence polynomial of the complement. So there are cases where the clique polynomial has only real root.